Fine. So we were dealing with Unit 5 drugs acting on central nervous system, and as part of it, we are about to discuss general anesthetics, narcotic analgesics, and NSAIDs, non-steroidal anti-inflammatory drugs in this unit. Then we have started with classification of general anesthetics, right? The general anesthetics classified into inhalational anesthetics and intravenous anesthetics. So inhalational anesthetics mostly halogenated hydrocarbons, halothane, methoxy fluorine, enfluorine, sevoflurane, isoflurane, desflurane are the examples. Intravenous anesthetics, ultra short acting barbiturates are methohexital sodium, thiamyl sodium, thiopental sodium. And dissociative anesthetic, the example is ketamine, hydrochloride. We saw the structure of halothane, which is an ethane on one carbon, three hydrogens replaced with three fluorines, and the second carbon, one hydrogen replaced with bromine, the other hydrogen is replaced with chlorine, and you have third hydrogen retained. So that is the structure of halothane. And the synthesis occurred from trichloroethylene, where it is subjected to condensation with hydrogen fluoride at 130 degrees centigrade, and followed by adding the bromine. By undergoing bromination, it will give us halogen. Moving forward, we'll see the remaining chemical structures. The next one is methoxy fluoride. So it is also ethane. So here you have hydrogen retained, two chlorines. In this carbon you have fluorines, two, and here you have OCH. So this is methoxy and fluorane, two fluorines and alkane. So this is the structure of methoxy fluorine. Okay, it is used for light anesthesia and muscle relaxation. Light anesthesia and muscle relaxation. During surgical procedures. If you see the structure of enfluorine, it is an ether. It is an ether. Carbon, carbon, oxygen linking another carbon. Right? So if you see hydrogen, fluorine, here it is fluorine, here it is fluorine and fluorine. Okay. Here you have one fluorine, second fluorine, and the hydrogen. So if you observe, if you compare methoxyfluorine and N-fluorine, here one chlorine is replaced with one fluorine, okay, and remaining this part, this side part is same, okay. Here ether link is there, here it is ether linked to CH. So here the ether is CH3. In CH3, two hydrogens replaced with two fluorines. So this is how you can compare methoxyfluorine and N-fluorine. So what is the use what are the properties of N-fluorine as inhalational anesthetics? It provides rapid induction. Okay, provides rapid induction. And one must remember that it should not be used in patients with convulsive disorders. If a patient is suffering with convulsions, that in such patients, N-fluorine should not be used. Not be used in convulsion disease conditions. Okay, so this is about N-fluorine. Then coming to sevoflurane. So it is also an ether. So you have three fluorines here to the first carbon. To the second carbon, one hydrogen and trifluoromethane, CF3. Here you have two hydrogens and one. So sevoflurane have trifluoromethane. It is an inhalational anesthetic. So this is the difference. Point for comparison. And let us see the structure of isoflurane. So it is also an ether. Carbon 1, carbon 2, ether link, carbon. So here same like sevoflurane, first carbon is having three fluorines. Second carbon has one hydrogen and one chlorine instead of CF. The third carbon is having two fluorines and one hydrogen. Okay, so please compare with the isoflurane. Here chlorine instead of CF3. Okay, here extra fluorine instead of one hydrogen. The differences between sevoflurane and isoflurane. Coming to desflurane, let me write the structure of desflurane. Carbon 1, carbon 2, ether, carbon. So three atoms attached to first carbon of fluorine. Second carbon you have fluorine and hydrogen. Third carbon you have two fluorines. And one hydrogen. So isoflurane is an isomer of N-fluorane. You observe N-fluorane and isofluorine, both are isomers. So this is about the hydrocarbon inhalational anesthetics. You have to compare which halogen is present in what compound. Okay. So then moving on, let us see short acting barbiturates. Ravina. Intravenous short acting barbiturates. So first one is methohexital sodium. So let us see methohexital instead of salt form. There are three carbonyl groups because it is not the salt form. So you have CH2, CH, double bond CH2, CH, C triple bond C, CH2, CH as the site. So it is very useful as short surgical operations for anesthesia. Okay. You see the synthesis of methohexital. The starting material for the synthesis of methohexital is diethyl malonate and 3-bromo propane. To see the structure of diethyl malonate. CH2 C double bond O C2 H4. So this is diethyl malonate. Added with 3-bromo propane. So this is the third position because the double bond gets the priority. So it is prop E in 3-bromo prop E. Okay. So what we add? We add sodium methoxide, C2H5ONA. This is sodium methoxide. Undergoes condensation, and you will get this intermediate. That is 3-bromo propanyl group goes and gets attached to diethyl malonate moiety. So let me continue in the next page. After the starting material, let us write the first intermediate, that is okay. So the propenyl group comes and gets attached here. Okay, to this intermediate, excuse me, to this intermediate, we have 2-bromo 3 hexyne. That means the second side chain. So what is it? 2-bromo 3 hexyne, and we'll add ethanol. Okay. So what is the strategy we are using? To the malonate ester, we are first adding 2 side chains. We are adding 2 side chains. Finally, we'll cyclize it to get methohexital sodium. Okay. So the next intermediate we get is the second side chain getting attached to the malonic ester. Some space. First write the malonate moiety. Okay, to this we have added 2 side chains. That means they will result in the 5th position. I'm just extending the branch up, but it is linear. CSG. So this is the intermediate we are getting. From here, what we do, we add N-methyl urea. This is urea, which we have CH3. This is N-methyl urea, and we'll use base NaOH for sodium salt. And N-methyl urea and the intermediate gets condensed and cyclized to get methohexital. Then the methohexital, as we have added sodium hydroxide, becomes the sodium salt, that is methohexital sodium. O minus, two side chains. One is CHCH3, C triple bond C, CH2CH. The other one is CH2CH propene. So this becomes Methohexital sodium. So this is the synthesis of methohexital sodium. 19DH96. Please mute yourself. So this is the what we are doing in same approach, retrosynthetic approach. So we know the structure of methohexital. Fine. So this is the structure. So what we are doing, we are taking this part. Okay, malonic ester. And to the malonic ester, in the first step, we have added propene group through bromopropene. And next, to the next intermediate, we have added this side chain. Okay, that is bromohexane. Okay, bromine being a leaving group will attach the both side chains at this position. After making ready this moiety, this part, what we are doing, we are taking N-methyl urea so that we can get this moiety. And N-methyl urea gets fused to malonic ester moiety and they will cyclize in order to form methohexital. And in order to get sodium salt, we'll add strong base, that is NaOH, so that we'll get here a sodium salt. Here, so that is the synthesis of methohexital sodium. And now let us see the structure of thiopental sodium. Sorry, thiamylal. Let us see thiamylal first. So you know the general structure, how to write barbiturates, urea moiety, and two side chains at fifth position. So one side chain is propene, the other side chain was hexane in case of methohexital, but let us see what it is here. Here it is pentyl group. So this is the structure of thiamylal sodium. Let us see what happens if it needs to be called as thiamylal sodium. If you observe the name, thia indicates sulfur, right? So here what we are doing, we are replacing oxygen with sulfur. That is the difference. Okay, so this is thiamylal sodium. Let us see if it exists in sodium salt, what happens. So you need to remember the difference in this structure. This is simple thiamylal, and if you need to write the thiamylal structure, so I'm depicting only the front portion. Mute yourself. So here the double bond goes off, only sulfur remains. Sulfur will be minus as it have excess electrons, and sodium is the positive. So this portion I have depicted. So this is how you will write sodium salt. If you don't mention sodium, you will write this structure. Okay. So that is the difference between thiamylal and thiamylal sodium. So next, let us see the structure of thiopental sodium so that it will be easy to compare. First, I'll write the structure of thiopental. So it is also a derivative of barbiturate. So this is the basic structure of barbiturate acid. Okay, this is the basic structure of barbiturate acid with two substituents here. One is ethyl, the other one is the same as that of thiamylal, that is pentyl. What is the difference here? The second substituent is ethyl group instead of propynyl. Right. Here it is propynyl, here it is ethyl group. That is the difference between thiamylal and thiopental. If you observe, this is an amyl group. Amyl group, what it is? 5-membered, 5-carbon containing group with one penultimate. That means the last carbon is attached to the is like branched. Okay, that is amyl. So that is the reason amyl, thiamylal. But here pental, he called amyl as pental, and the difference is ethyl group when you compare with that of thiamine. So how do you write thiopental sodium? If you want to write thiopental sodium, remove one double bond here, O minus. So this sulfur being sulfur instead of oxygen, thio. Yes, this will become thiopental. So that is how you write thiopental and thiopental sodium. That difference should be clearly shown. If it is not sodium, you will have double bond S. If it is sodium, you will have single bond S minus, and you will add cation sodium. Is that clear? And we have the last candidate, that is Catamaran hydrochloride, the dissociative anesthetic. Ketamine salt form hydrochloride. Okay, so how it looks like? This is a phenyl ring having a chlorine attached to cyclohexyl ring. This is cyclohexyl ring. And if you put double bond O here, this is cyclohexanone. And here you have NHCH2, ethylamine substitute. And this is a salt of hydrochloride, so HCl. This is the structure of ketamine hydrochloride. So we need to learn the synthesis of ketamine hydrochloride. So starting material for the synthesis of ketamine hydrochloride is alpha chlorobenzonide. So observe the chemical structure. I need a starting material for this form. So cyano is a easy leaving group. Okay, so alpha chloro benzonitrile, benzonitrile, and you will use Grignard reagent. What is Grignard reagent? It is RMgX. R means alkyl, Mg is magnesium, okay. X is halogen, either chlorine, bromine, fluorine, or iodine. So that is the general formula for Grignard reagent in general. So particularly in this reaction, we are using this one. I'll show you. What is that? Bromine, okay, halogen, that is X. Mg is an atom, okay. Then R. This is cyclopentyl. So cyclopentanyl Grignard. This is cyclopentanyl Grignard. Okay. So it's a simple protonation and condensation. What happens? Grignard comes and attaches to alpha chlorobenzonite. Here, C carbonyl group. Okay, nitrile is converted into carbonyl, and this is a cyclopentene from Grignard. To this, we'll add bromine. This will add bromine. What happens if we add bromine? Bromine comes and gets attached to cyclopentene. So here, to this part, we need to add bromine. Why? Later we'll replace bromine with the NHCS3, methyl amine. So we'll add methyl amine. C double bond N C double bond N CH. And here you have cyclopentene, to which you have OH. Bromine is replaced with OH. So what happens here? A 1,2 shift happens. Rearrangement happens. Loss of protons. What happens? This double bond shifts here. Okay. And hydrogen observe there. Okay. That bond will be shifted, and the bond from cyclopentanyl comes here. So that means ring expands to get Catamaran hydrochloride. This OH will become C double bond O as proton is lost. This proton is lost. Comma 2 shift. So what is happening? First, alpha chlorobenzonitrile is added with Grignard, where we are taking advantage of cyclopentanyl. Okay. and carbonyl and cyclopentanol comes in. There we are brominating. After brominating, we are adding methylamine, where methylamine gets attached and bromine will be replaced with the OH group. Here at this position, 1,2 shift happens where cyclopentanol ring will be expanded to cyclohexenyl ring, and the OH, from OH it will be converted into carbonyl. Alcohol will be converted into carbonyl group, and finally NHCH3 substituent is attached at the required position, which gives us ketamine hydrochloride. Hydrochloride is just a salt. Okay, so this is the synthesis of ketamine hydrochloride, and with this we have completed general anesthesia. So that is it for today.